So we're going to talk about math for AI, in the next maybe, 30 to 45 minutes, depending on how fast we can go. And did I mention this? Machine learning is really computational statistics. Can someone tell me, what does that mean? Like statistics, what does that mean? Okay, a lot of data, right? There's a set, and also ways to analyze them, ways to understand them. Yeah, that's pretty good. Yeah. What is computation statistics? What does that mean, computation statistics? It's really basically using computers to do statistics, as opposed to, for example, I think, prior to the invention of computers, we're trying to find, quote, quote, analytical solutions, right? That's how, for example, physical science was actually, developed, for the first couple hundred years, right? But right now we enter this era where everything we're using, we're using computational horsepower that these computers give to us to find insights in data, right? So that's what a machine learning means, computational statistics. So today's agenda, what we're going to do is we're going to talk about, as I said, just 3 topics, pretty simple, right? We're going to talk about linear algebra, probability, and statistics. All right, so linear algebra, pretty simple. We're going to talk about vectors, matrices, and their operations. So vector, is basically, this thing that has a magnitude and direction. And one example could be velocity, right? So that's in physical science, velocity as opposed to speed. You can travel, 85 per hour, 85 mile per hour. Okay, 85 mile per hour is way too fast. 25 mile per hour, right? The speed. But you could say, I'm traveling north, 25 mile per hour, right? So that concept has both a direction and a magnitude, and that's a vector. And later you'll see how vectors are used, in machine learning. And vector can be represented, just by a list of numbers, right? So for example, right, this A vector here, right? So you imagine you have this, X and Y plane, right? So the X would be horizontal axis, Y would be a vertical axis, right? And this vector, 4, 3, literally just like the coordinates of the endpoint, right? So forming this, vector by connecting the origin and that coordinate, right? So it's point upright, okay? But you can also have the minus A, which is basically the opposite direction of A vector. And so that's -4 and -3, okay? So bear with me. This is AI camp. Why the hell Michael is talking about math? So example vector, right? As I said, a direction, right? 1, -3, a ship is traveling southwest. Well, here we go. Now we have actually, something that relates to machine learning, or natural language processing, okay? Remember, the computers doesn't see words, right? Doesn't see pictures. Pictures are just pixels, right? And the whole, when you look at sentence, my app just passed the Turing test. Anyone heard about Turing test? Yeah, do you know what a Turing test is? Yeah, okay, good. So what we're doing right now is we're basically turn each of these words into a number, and these numbers are called tokens. Okay, so it's almost like, what's the you basically take each one of these words and you look up its order in the dictionary. Okay, and that has a number. So the reason why we, for example, want to turn these sentences into these numbers is, it could be, for example, you can represent a sentence using just a vector. And you can also calculate, for example, how 2 sentences are, differ or similar to each other to look at the difference between their vectors. Okay, so that's another way to think about it. A matrix, right, is something that, just a vector, a rectangular array of numbers, right? So in this case, we have actually, 3 by 3 a matrix. And then each element, you guys see the element, 1, 2, 3, 4, 5, 6, right? Each of these things are just called elements, right? So these are elements. Another important concept when you're dealing with matrices are basically the dimensions, okay? Because they are just rectangular array of numbers, right? So they naturally have these concepts called rows and columns, right? So we have, 2 rows here and 4 columns here. And therefore, the dimension of this matrix is 2 by 4. Okay, pretty simple. Do you think a vector is also a matrix? A vector is a matrix, okay? It's actually a special kind of matrix. One of the dimension is just one. If you, for example, mapping, this simple vector into just rows, number of rows, right? So that's n by 1 matrix. So vector is also a matrix, just a special case. Okay, so matrix, you can have different operations. You can add them together. You can multiply them together. You can inverting and finding the eigenvectors and eigenvalues, transpose. We're not talking about, the bottom categories. We're going to talk about adding and manipulation. And you will see how, for example, these matrices operations, they are associated with deep learning, right? So we'll see that. So if you want to add in two matrices, together, it's exceedingly simple. You basically just add them element by element, okay? Do you see that? What's the order of A again? Yeah, it's 3 by 2. You count the rows first, right? Count the rows first. 3 rows, 2 columns. And you have B also 3 rows, 2 columns. And what you do, you just add element by element. So if you look at C, right? You see the 7 there, right? In the second row, first column. That's equal to the second row, first column, plus the second row, first column of A and B, right? 3 plus 4 equals 7, right? Pretty simple, okay? So adding matrices together, you just add that element by element. Now there's this concept of dot product, which is basically, two matrices, multiply together, okay? Multiply together. And the way you, carry out that operation is you literally take a row, okay, you take a row and you rotate it, okay, rotate it. You line up with the second matrices and you just imagine you multiply together and add together. Okay, one more time. You take that A, right, rotate it, match it with the B, and then multiply and add together. See that? So that's why you have AX plus times BX plus AY times BY plus AZ times BZ. You got that? That's pretty simple, right? For the, 1 by 3 times 3 by 1. Now, another thing that's pretty interesting here, right, is A is 1 by 3 in terms of order, and B is 3 by 1, okay? Because you're gonna do this rotation, then you can only multiply matrices if the inner dimensions, they match. You got that? Okay, you can only do that. And also, when you're doing the addition, these two, because we have to add them element by element, each of these matrices, they have to be basically matched by the dimension in order for us to do the addition, okay? So again, right? In the case of the multiplication, you have to match them. The inner dimension has to match. Right, so things can quickly get out of hand if you have more than, for example, like just one dimension in one axis. So look at the bottom example, okay? A, B, C, D times W, X, Y, Z, okay? Again, you focus on the first row, which is AB, right? You rotate it, okay? You rotate it, and then what you got is A times W plus B times Y, and that's the first element, right? And then you go to the second, right? The second element or second, I guess, column, right? In the second matrices, right? Second matrix, you rotate A, B together, right? And then you have A times X plus B times Z, and that's the second element. Okay, so on and so forth. And this is how you basically multiply these matrices together. The only thing we have to remember, okay, has to do with deep learning, is basically the inner dimensions they have to match. Okay, let's do the following. 1, 3, 2 minus 5, A2, 1, 3. You see those two matrices? Here I wrote, you take the first row, which is 1, 3. You rotate it, right? So once you rotate that, it's 1 times A plus 3 times 1. You see that? They give you the first 11. Do you see that? So let's see if we can do this. So you got a 1 and 3 here, right? And 1 and 3 here. Now you want to rotate a 1 and 3. So you just want a 3 right now. But if I rotate it, right? If I rotate it, it becomes like this. This is 1 and 3, right? And what we can do, let's just change the color of this thing so that, where that come from. This 1 and 3, you rotate it, right? And then you come over here, right? Okay? You come over here and you multiply 1 times A plus 3 times 1. They'll give you the first 11. You see that? And then you have the 1 and 3, and then you go to the second row, right? So that's 1 times 2, right? Plus 3 times 3, they give you the second 11. See that? And then you can have, of course, right? 2 and minus 5, right? So that's the second row. Second row, we rotate it. You go to the first one, right? And you have 2 times 8, that's 16, minus 5. So that gives you 11, which is this first 11 here, right? First 11 here. And then you do the second row, right? So that's 2 times 2, go to 4, minus 15, so that's minus 11. That's this guy. You got it? Pretty simple, right? Not that confusing. Okay, good. So matrices are everywhere in deep learning, right? You probably, look at this graph, which is basically what? The different neurons, right? Each one of these circles are the neurons, right? The weights can be represented by vectors, okay? Weights can be represented by vectors. Okay, hear me out though. You look at the second layer of neurons here, right? Second layer of neuron here. Do you guys remember for this neuron, the value of it? How does that value come in again? You look at this guy, right? You look at how many neurons are connected to it. So, W11, right? And W21 connected to this guy. So the value of this neuron is very simple, okay? It's I1 times W11 plus I2 times W21. You got this value, okay? Again, it's I1 or W11 times I1 and W21 times I2. You got that? Add that together. And that's this guy right here. W11 times I1 plus W21 plus times I2. See that? Do you guys see that? You basically have a vector, which is the weights vector, times the input vector, give you the output for these neurons. You see that? You see how these matrices operation results into that, right? So, and when you look at W, right, which is the weights, is 2 by 3. 2 input neuron to 3 output neuron, 2 by 3. Input, okay. I got something called 2 by 3 by 2. No, I got something wrong here, right? So it's 3 by 2. This is 3 by 2, right? 3 by 2, and this is 2 by 1. Okay, and that's why it's 3 by 1. I didn't know why last time I didn't really catch this, right? Because the weights are 3 rows and 2 columns, right? So it's 3 by 2. The input is 2 by 1, 2 by 1. So you get rid of the middle one, you get the results of 3 by 1, right? So 3 by 1. Okay, you see that? That's this layer. Okay, so this is why we're using GPU for deep learning, right? Graphics processing unit, because they're insanely good at multiply different matrices together. Okay, they're using hardware to accomplish that. So now we're gonna move on. Okay, we're gonna talk about probability and statistics. So the first thing to understand is this concept called random variable, right? This is maybe pretty confusing stuff, but random variable is as opposed to a variable that's for sure that's gonna happen. For example, your age right now, right? So maybe Shahab is 17, right? That's a variable that we have a defined value. Okay, but random variable, the value depends on random phenomena, right? So a very simple concept could be tomorrow's weather, right? Whether it's like sunny, cloudy, we don't know. It's kind of random. It depends on so many factors. We don't have the ability to predict that 100%, right? Sometimes it's due to our lack of information, right? Sometimes it's really due to for example, you observe something, your observation will change the outcome itself. That's actually the basics for quantum mechanics. Now, the example of random variable, right? This is you guys heard about this company called Tesla? Right? They make pretty cool products, electrical vehicles, right? And you can see basically the stock, goes up and down. Yes, there has certain value, but for the next day, what's the value for Tesla? We don't know that, right? It could be $1,000. I think right now it's $1,500 or something like that. That's kind of crazy, right? Because we didn't make this slides like a year ago. We made these slides, looks like in the summer. And oh my gosh, it's like, grew so much. So probability is basically the chance of something that will happen. That's a very simple way to explaining it. But later you will see, different school of thoughts of how to interpret, probability. But for now, we're just going to stick to this. That is the chance of something will happen. An example of probability, for example, chance of getting 6 when rolling a dice, 1/6. Because the way that we kind of processed it is like, oh, we assume the dice is fair, and the chance of getting every single phase, therefore, is equal. And there's only 6 possible chances, so it must be 1/6. The chance of getting heads in a coin toss, of course, without asking, I know you guys will say 1.5, right? Assume the coin is fair. What about the chance of Tesla stock drop to 0? So it could be pretty low, but there's a certain amount of chance. There are a few probability rules, okay? And understand these rules, will help us, in this class. So probability has value between 0 and 1. Probability has value between 0 and 1. 0 means impossible, right? 1 means like certainty, right? And 0.5, of course, even chance, right? So you can see it's restricted between 0 and 1, okay? Things can never above or equal to 1 in probability. The rule number 1 is all the possible cases that add up equal to 1. That is, if you're rolling a dice, the dice has 6 different faces, right? And therefore, P1 plus P2 plus P3, adding all the way to P6, that must be equal to 1. And if you assume every one of them is equal, then you have 6P equal to 1, and therefore P equal to 1/6. That's intuitively how you did the calculation. So probability adds up, all the scenarios equal to 1. And that has very simple but nice consequences. And this is one of the things you probably want to think about when you make certain decisions, okay? That is, for example, the probability for something that's not A that's going to happen is equal to 1 minus of A happening, right? The probability of not getting to phase 1, rolling a dice, is equal to 1 minus the probability of getting that phase equal to 1. Therefore, it's 5/6. Pretty simple, right? Another thing that we need to understand is this concept called sample space, which is basically when we think about certain events, what's the total ensemble of things that's going to occur? So when you think about rolling a dice, there are only 6 outcomes. So those 6 outcomes are essentially our sample space. And when you think about the emotion detector, there's only 5 emotions we can detect, right? And that's the sample space for the emotion detector. Now, the sample space for our ASL, American Sign Language, or the Dream Team. So having these concepts helps us to understand what is a mean and variance, okay? So if we have a sample, the mean, right, is basically you add up all the numbers and divide it by the total number that you have. So for example, if we, do a mean of our age in this interaction or this group here, we're gonna go somewhere around like 16, 17, somewhere there, right? So that's mean. Have you guys heard about this thing called a median, right? Is you first get all these samples, you line them up, and you basically, place order, right? From the smallest to the biggest. Once you line them up, you basically, if we have 20 people here, we count, 10 right here in the middle, right? Or maybe 21 here. And so you have 10 this side, 10 this side, and we'll look at the 11th one. And you look at what's that number? That's median. Median is different than mean. Do you see? If we, for example, just in case, all right, we have someone who's like a mini-year-old. By the way, I'm maybe a dinosaur. I'm a mini-year-old, right? I'm like really, really old. And then I can calculate this group. Just say, if for example, I'm 1 mini-year-old, and we calculate the mean, and we calculate the median for this group. Do you think the mean is bigger than the median? Or the mean is smaller than the median? Or the mean is equal to the median? So think about this, right? The mean, you have to add all that number together and divide it by the number of people. Now, because I'm a million years old, your age almost doesn't even matter, correct? There's a million divided by 20. Now, in terms of median, however, you line them up. You line everyone up. So I would be, this like here, really, really tall. You guys would be like, so tiny. but you just count in the middle, right? And so this tall guy doesn't really matter, doesn't even take into account. So your median would be still around 16 or 17, right? So you basically compare a median divided by 20 versus 16, 17. Which one you think is bigger? All right, so let me do one more count. In that last example, do you think the median is smaller than the mean? Then raise your hand. Yes, that's the case, right? Because as I said, the median, right, is still staying around 16. The mean, however, is huge, okay? All right, it's important to understand what's the median and the mean though. As you will dive into data analysis, you need to understand that. And then the variance, okay? So variance, look at this formula. Do you think this formula is intimidating? But don't be, right? It's not that intimidating. It describes the spread of your random variable, right? And the way to think about this, you see the mu there. The mu is basically the mean, right? So what you're doing is basically you say, all right, so we sort of like just say have the sample here, and we look at the average, right? And we look at the difference between each of these dots to the average, right? Look at each dot of the average. But then, each of the difference, they can be positive or negative. So what if we just want to treat it equally? Just look at the distance, right? Well, one thing you can do, you can square them, right? Square them. And you add that difference together, right? Or square the difference together and divide it by the total number of sample, right? That tells you how far apart each of these dots are away from the mean, right? So if the dots are all close together, then what happens is, the mu is close to every other samples, right? And that means the variance is small because the difference between them is small. The square is also small, right? You divide it by the same m, doesn't matter, it's variance small. But if you say you have a huge, sparse sample, it's spread out, it's spread so much. So each of these dots to the mean would be far away, right? You square them, that would be far away. You average them, they will still be pretty large, okay? So variance in that case is pretty large. You see that? Okay, so variance really describe the spread, okay? And you will go ahead and look at those statistics when we are analyzing the COVID-19 data set, okay? Another interesting concept, and this is something you will plot as well. For example, we're going to plot the income for different cities, right? And we're going to examine for different cities and look at how's the socio-economical conditions, maybe can be a predictor in terms of how COVID-19, badly hurt them or not, okay? And what we're plotting here is basically the distribution, right? The distribution, the way to understand it is basically, you see the number of heads, basically doing a coin toss, right? Coin toss. Well, one coin, we toss it 10 times. What's the most likely thing's gonna happen? If you toss it 10 times, you count the number of heads. What's the most probable outcome for the number of heads?
5.
That's right. And you see the 5, that's the highest bar there. See that? What's the chance if you have all 10 heads?
Unlikely.
Very unlikely, right? You see that? So that's why on the right hand side, it's so unlikely, right? It's 1 divided by 2 to the power of 10. What is 2 to the power of 10 again?
1024.
1024, 1024. 1 divided by 1024. Oh my gosh, that's really, really small, right? That's like 0.1%. Gosh, that's really small, right? So the distribution, right, is literally, okay, you do the following. You basically say, let's just do this 10 coin flips 1,000 times, right? You do that 1,000 times. And you count, okay, how many times you got it? 5 heads. How many times you got 10 heads? How many times you got 4 heads or 3 heads, so on and so forth. And then what you do is you get all these numbers, how many times you get 10 heads or 5 heads, you divide it by 1,000, right? Because that's the number of times you tried. So that gives you the probability for that to happen. and we intuitively understood things going to happen more often. They're going to show up, more prominent in this distribution thing. Do you see that? Okay. So a distribution helps you to understand in relative terms how things gonna, be likely happening or not. You got it? So there's been more interesting talks or more interesting distributions. So on the left-hand side, this is, when you look at daily total precipitation, right, over some place, and you look at basically the probability of that will happen. So looks like this place, many days, the most probable day. Okay, actually, let me ask you a question. When you look at the distribution on the left-hand side, what is the most likely things going to happen for this city, for this place, in terms of weather?
There's not going to be any precipitation.
That's right, right? There's no precipitation, right? It's going to be dry, right? And the chance for something like 80 millimeter. Do you guys know how deep is 80 millimeter? I guess, we're in the States, and so we're using strange systems, inches and feet, right? The rest of the world, they move on to metric systems. It's about 4 inches, right? That's right. So the chance for you to have 4 inches, precipitation or rainfall, right, is pretty small. Okay, it's pretty small. And what people are doing here, they're fitting it, right, with some probability distribution. Okay, it's called a gamma, right? Gamma. So there are so many different distributions, which you will learn later. We're not a teacher in this class though. Okay, on the right-hand side, do you see on the right-hand side? This is also a probability distribution, right? This is basically saying, okay, well, I have 2 dice now, 2 dice. And I have one that's black, one that's white, okay? And I'm looking at the probability distribution of the sum of the dice. So obviously, the way for me to get, total dice equal to 2, right? That's just 1, 1. You basically have those 2 coming together. Do you guys know why that's 1 divided by 36? Basically, what's happening is we know you flip the black dice versus you flip the white dice. Those 2 are independent events. They're not affecting one another, right? So, and therefore, the combined probability is just equal to probability A times probability B if 2 events are uncorrelated. You got that? So which is why 1 divided by 6 times 1 divided by 6, which is 1 divided by 36. Okay? And then, of course, right, the ones that are going to happen very often, surprisingly, is actually number 7, because there are multiple ways to have number 7. 1 plus 6, 6 plus 1, right? 5 plus 2, 2 plus 5, 3 plus 4, 4 plus 3. And that's why, you're adding all these things together, every single block give you 1 over 36 probability, right? So when you look at, to get the sum of 7, there are actually 1, 2, 3, 4, 5, 6 different ways. Each one of them give you 1 over 36 probability. So the total probability is 6 divided by 36. Okay, all right. This is the distribution of declared COVID-19 cases in Iceland and Netherlands by age group. What conclusions can you do when you're looking at this plot? You see the Netherlands, skewed to the right-hand side, which are elder group, right? So in terms of proportions, right, you have more cases in Netherlands that are for people above 59, right? Relative terms than people in Iceland. So we also sometimes looking at these statistical summaries. We already talked about distribution on the left-hand side, right? Sometimes we're also going to look at the 5-number summary. So we look at the median, the mean, the standard deviation, the 25% distribution, the 75% percentile, right? So those are 5-number summary. We're going to look at confidence intervals, okay? That is, describe what percent of time or real data point would fall within your estimation. The 95% confidence interval would be like, I'm 95% sure, the real value will be in this interval. Okay, so these are different basically statistics that you will actually encounter when you actually go and analyze the COVID-19 data set, which we will do in the next hour. Okay, so why do we need to learn all these? Because machine learning, as I said, is really about pattern matching, right? When you think about machine learning, right, it's really about finding these patterns in data and recognize these patterns in data. Traditional machine learning, okay, so which we're gonna learn in the second week, and we're gonna prepare the data now, is really about handcrafting features that might correlate with outcomes. Sometimes crafting these features are like more art than science. So for example, let's just say we wanted to analyze the COVID-19 data set and see how it's actually impacted our communities differently. And the whole reason, for example, we went to that direction is because we heard news report that COVID-19 hurt poor communities more than it hurt richer communities, right? We sort of knew that. And then what we did was we went ahead and tried to find data, right? Like socioeconomic data for different cities. We look at education, right? We look at unemployment rate. We look at poverty rate. We look at income, okay? And see if those predictors or features, see how those things will predict if COVID-19 is hurt that community, more than average. You see that? So we have to sort of like intuitively try and understand, what kind of things might hurt those communities, and actually go and find those things. So we're handcrafting those features together. However, in neural network, this is a game changer. Traditional machine learning is really the old paradigm. The neural network, okay, I'm listing here, but I'm gonna explain them a lot more in details. It's an end-to-end learning platform that uses internal representations to craft features that correlate with the outcome, okay? So what I mean here is that in neural networks, you don't have to handcraft those features anymore. Neural network take all your inputs, okay? And they're basically like inside of it, they're updating these weights so that the deeper the neural network you get, these features, they correlate with the outcome you want. So they're crafting those features internally, okay? That's a key difference. So correlation, what do you mean, Michael, correlation? How do you define correlation? So for example, a correlation is just like asking if the two random events are related. Intuitively, of course, flipping the two dices, they're uncorrelated. But if you have a bad weather, you might have less solar power. That's correlation, right? No social distancing results into more COVID-19 cases. A kindergartner can understand that. Our president doesn't, right? So these are correlated, because of causation, right? But you could also have cases, they're correlated, but they're not causation, okay? Do you guys know Nicolas Cage? Anyone? Nicolas Cage? Some of you do, okay? Some of you don't. But that's just a crazy actor, right? It's a crazy ass actor. And you can see here, the number of people who drowned by falling into a pool somehow correlates with the films that Nicolas Cage appears in. I mean, of course, those two are not related, right? But somehow they're correlated, right? I thought it was pretty funny, this whole thing. It's sadly funny though. Yeah, so correlation does not imply causation, okay? It does not imply that at all. And so this is something also you wanted to, constantly watch, in your life. That is, something that's correlated doesn't mean causation, right? You need to think deeper, than that. And quantifying correlation, there are these correlation coefficient, which I'm not gonna go into it, how we're gonna calculate it. But if two events are they're independent, what do you think about the correlation?
Unlikely.
It's zero, right? Because they're independent, they're not correlated. So PAB equal to PA times PB, the numerator is zero. So this correlation coefficient is only a linear correlation, okay? It only describes how spreaded, right, your data set is. So for example, we have, X and Y here, right? And you can see, the first one, you have, X and Y, they're perfectly correlated because they're lined up into a line. Doesn't matter what the slope is, this line will still, give you a correlation equal to 1. As I said, it only describes the spread of the whole thing. And you can see the middle here, X and Y, it look like X doesn't depend on Y at all, right? That's why the correlation is 0. but you can also have these funny shapes. They are probably correlated in some fashion, non-linear, right? Non-linear. But yeah, you can see like, you see the right-hand side, you see there's a circle here. That's definitely correlation, right? It's definitely correlation. But it's not correlated in a linear kind of fashion, okay? And the correlation coefficient still is 0. So this correlation coefficient doesn't really tell you, for example, the whole thing is correlated or not. It just tells you it's not linearly correlated. So as I said, traditional machine learning is really about finding those features that are correlated with the target, right? Usually requires years of domain knowledge, right, to craft those things. It's really slow, it's inefficient, it's an old paradigm. Although we're gonna try it anyway, okay? Because in terms of deep learning, right, we also need these correlation. So for example, we are looking at this beautiful, classic car. I don't know what kind of car it is, but it looks pretty cool, right? And the first thing we do in the neural network, okay, so we're gonna do these visualizations quite a bit more, but the low level features are just those lines and contours, lines, and just those contrast lines. Do you guys remember in the intro to deep learning one, I showed you the video where they poke into the brain of a cat and to map the visual field? Do you remember that? But these low level features, right, they're just really looking at these contrasts. And then what you can do, the second layer, remember the second layer combine what's in the first layer. The second layer was able to combine these different lines and contours and form these different shapes, right? And then once you have these shapes, you can combine them, right, into different geometries or patterns, okay? Do you see down there, there's this bird-like thing, right? The bottom row, second one, you see those bird things? You see like the first one looks like a honeycomb, right? These are just combining different things from the previous layer, go to that layer, okay? And then eventually, it's really about looking at those features and how these features maybe have different, weights, and see how that results into, oh, that's a car, right? And, for the gun fishing team, right? We're looking at basically cluttered versus uncluttered space, right? To settle down the dispute, between parents and kids by siding always with the kids. What we're doing, right, is we look at these different contours and look at go all the way to these high level features. What's gonna happen, right, is, oh, the clean ones, they always have these clean lines, right? They don't have, for example, all different, these features together. And we know those are clean spaces. And that's how we're gonna classify clean spaces. For the ASL, for the team, it would be like, oh, different hands, maybe different contours and different things. And then somehow you're combining these different contours and things that will give you, oh, that's letter A, right? For different currencies, same deal. You see, deep learning is using hierarchical composed features and see how those features are correlated to give you predictions. Do you see that? So, for example, if I wanted to do the emotion detector as example, right? Another example, you see the raw data, which are the pixels. You can analyze them on low-level features with the edges, and you have different face parts coming together. And then finally, high-level features that basically give you different maybe emotions, right? That's essentially the level of progression of features within a neural network. Of course, I'm just giving you a simplified picture and a really ideal world examples. The reality is once you get to the lower levels, we have no idea. I mean, higher levels, we have no idea what we're looking at. Okay, because it's actually pretty hard to see it. We're probably gonna put another lecture together to give you more visualizations within the neural network. Okay, but that's gonna happen in the third week. Okay, so review of the concepts. AI, right, is equal to math or computational math. Linear algebra, we'll talk about vectors, right? They're just, ensemble of numbers. Vectors as magnitude and direction. Matrix, right? We talk about order matrix. We talk about different things in this matrix. We'll call them elements. The dimensions are just a number, just a number of rows by number of columns. We talk about matrix operations, such as addition, elements by elements, and dot product, right? Which is basically, you take the row, you rotate it, right? You times that column and add them together, right? We talked about how those things relates to, you know, deep learning. We talk about probability and statistics. We talk about this concept of random variables as opposed to, you know, for sure variables. We talk about probabilities, chance of that those things will happen. We talk about distributions, right? To look at in one graph how likely, right, those things will happen, you know, compared to the rest of it. We'll talk about correlations. Correlation doesn't mean causations. We'll talk about features and how deep learning or machine learning is really about features and find those features correlate with the outcome. But correlation doesn't mean causation. And we talk about, for example, deep learning, this new paradigm of machine learning, right, is really using hierarchical composed features, right, low level, middle level, higher level features. And we talk about, for example, all these things, they are, you know, end-to-end representation, and you don't have to do handcrafted features anymore. That's a lot to digest, but hopefully learn a few things, you know, during this whole hour.